Are we feeling pumped? Yeah?
Yeah.
Oh, we can do way better. All right, let's do it again. Are we feeling pumped?
Yeah.
Yes. So thanks, guys, for coming at 9 o'clock. Really appreciate it. I got the worst slot, but it's great to see a good audience. So what we're going to do today is to talk about this thing called Spark. So I'm going to introduce a lot of fancy words, you know, HDFS, big data processing, great for dinner parties. So that's going to be useful tutorials in that regard. And I'm going to spend perhaps maybe 20 minutes, half an hour, explaining some concepts, explaining the bigger picture, and then the remaining hour of this tutorial should be very much hands-on. So we'll have a Python notebook, we're going to write code, and get to learn the Spark API. So Cambridge Spark and Apache Spark have nothing to do with one another. It just happens that we share the same word, Spark, but we're not affiliated to the Spark project. But however, I am a big fan of Spark generally. So before I kick off, there's a few things to download and links to type in your browser. I'm going to explain what they are. So if you want the slides, here's a link so that when you go home or later over the weekend you want to refresh, you have the material. The second link is a Git repository that has the notebooks and data set that we're going to use throughout this tutorial. However, the coolest link of all of them, it's the third one. I set this up yesterday because I discovered Google has this service called Google Colab, which allows you to have a notebook in the cloud with everything set up. So normally, if you just click on this, then you'll see a link. So I'm just going to click on that. That's the one you really want to click on. So I'm going to click on it. And you should see something like that. So I'm the owner of this notebook. So I'm going to go into incognito mode. And I'll put the link back on the screen in a sec. But just so you see what's going to happen. So you're going to see this. And you should be able to click on Open in Playground. It does require you to have a Gmail account or a Google account. And what it's going to do is to store this notebook in your G drive, and then you can play all the code. So that installs Java, it installs Spark, and everything, configures everything, so you should be ready to go within 10 seconds if everything goes well. Okay? So I'm going to put the slides back on. So again, you'll have to click on Open in Playground once you signed in onto your Google account. So let me put this back up so everyone can just download this.
So we don't do we just go to the collab notebook or we get the files?
Well, what I recommend is you use that one, especially if you're on Windows, because it's impossible to get anything productive on Windows. Sorry, who's using Windows? I'm very sorry, guys. Feel your pain. But installing Spark on Windows is really tricky because you have to set up some environment variables and stuff, and it's, I just don't even know how to set up an environment variable on Windows. You have to click somewhere. Cool. So I'll give it another 30 seconds. So take a photo in case you want to come back to the slide in a bit. All right, can I get some thumbs up for those that have done it? All right, that looks like quite a lot of you, so let's get going. So in that repo, there's also manual setup instructions if you want to set things up on your laptop rather than on the cloud. So let me start with the bigger picture. Hey.
Could I hand you one of the wireless mics so that we can get it on video as you walk that way also?
Oh.
Sorry. Either that or we can hook you up.
I'll be coding, so I definitely.
Okay.
I don't want to hold a mic in my hand.
Fair enough. Yeah, sorry about that. Let's see. And that should be working now. Yeah. Okay. There you go. Thanks.
Whoops, sorry guys. All right, 1, 2, we good? All right, guys. So I'm going to spend maybe 20 minutes going from really high level to low level, explaining the landscape of what big data is, available technologies, and then focusing on batch processing using Spark. So I'll introduce a lot of new words. So before I get going, you always hear big data. These days, like AI, makes money, it sells, it's great for marketing and sales. So at Cambridge Spark, we decided to go next level. We're going to go humongous data. That's the new buzzword, blockchain compliant. Here we go. Humongous data it is. More realistically, I want to shed some light on why everyone's making a fuss about data processing generally and how do we scale that. So this is the context that we see in the industry today, right? So storage cost has decreased exponentially over time. So it's a commodity to store data in the cloud. It's really cheap. On top of that, processing data is also a commodity now, just in comparison to 10 years ago, right? We can get lots of CPU time on the cloud, and it's cheap. And finally, the bandwidth is also cheap. So if I want to exchange data with the gentleman with the hat, what's your name? Anthony. If I want to exchange data with Anthony today, it's really cheap to do that over the internet compared to just a few years ago. If you remember those modems that were making this weird sound, right? So we didn't have a lot of bandwidth and it was expensive. Now, as a result of all of this, you can see the odd one out. It's the network graph there that shows the number of interconnected nodes on the internet that has increased massively. So we have a ton more devices that essentially are producing data that is really cheap to store, cheap to process, and cheap to exchange. And that's why the tech industry has really been revolutionized. Now, to go a little bit more technical, and if I look at the trend on the microprocessor evolution, then what we see really interestingly is, over time, number of transistors, as you can see, still increase over time. So that means we can do more work. And we can see the number of cores here is also increasing. So that's how we stack up CPUs together to collaborate to solve a task. So that's kind of good, like we see progress. Now, you'll see like those three other lines in the middle are kind of stagnating. So how much power we can get in the chip, the frequency and the instruction level parallelism are kind of stagnating. So that means we can't get as much performance as we could from just one single core. The trick that we've been doing for over a decade now, and we've commentized it, is to have multiple core architecture. Now, I think this is really interesting because the same principle that we have on a single computer, a single server that has multiple cores is directly applicable to distributed systems. Suddenly, in order to get better performance, we're going to have to coordinate the work amongst multiple cores on one machine or amongst multiple machines if we go distributed. So conceptually, it's the same idea, and that's something we have to work with as developers. And obviously, there are new technologies that's going to help us facilitate this work, whether it's multiprocessing or whether it's distributed processing. So the context we have is we have a lot more data, we have cheap hardware, but we're going to have to go parallel and distributed to exploit the latest hardware that we have. So let me spend a bit of time defining big data, and then I'm going to focus on one specific class of problems in big data called batch processing, and then I'll introduce the Hadoop ecosystem. Now, if you're really interested in the computer science fundamentals behind distributed systems, I really highly recommend this book of Martin Kaplan. He talks about all those kind of engineering concerns that you might be interested in, like consistency, sharding, NoSQL database, how they all implemented, the CAP theorem. So just general good knowledge to have as a computer scientist. Now, the volume, just to put things into perspective, Facebook has 2 billion users, and conservatively, let's say like each user is making like a 1 megabyte contribution of data per day. So, Anthony, do you like to take a selfie now and then? sometimes, right? Who doesn't? So a good selfie in high definition, probably 5 megabyte already. So, this is very conservative, right? So just the status, the liking stuff, 1 megabyte of metadata. That's about 2 petabyte a day. And that's not even counting redundancy. So, in case some server crashes, do we have some backups about the data of our users? So it's even more than this, right? But just to put things into perspective, there's clear challenges with this amount of data. My computer, or Anthony's computer, is not going to be good enough to store all the selfies that Facebook users produce every day. So we're going to have to distribute the data storage over several machines, and we're going to have to figure out how to process this information over several machines as well in a way that provides fault tolerance in the case some machines goes down. So there's a lot of challenges to cope with the volume of data. The next concern is the velocity. So that's about the amount of information you receive right now. So when I speak to Anthony, you're receiving all this information and you have to process it like now in real time. And again, that puts a lot of challenges from an engineering point of view. So for example, the CERN, so particle collision detector back in Europe, we're recording 10 gigabytes of data per second, just to kind of keep track of particle collisions. Twitter indicated that they have 3,000 images per second that they have to process that are being tweeted around. And WhatsApp, 60 billion messages a day. So that's from a couple of years ago. So, you can probably multiply that by 10, I guess, now, right? So again, from an engineering and processing point of view, how do we build an architecture or infrastructure that's allowing us to cope with all this information in real time and it's distributed over several machines? Now, my favorite one is the variety, because that's the one as a data scientist that you see in practice. So who's a fan of Excel? Raise your hand. This is a safe environment. There's no shame. No, the doors are closed. No one will know. So can I do some basic correlation here? If you love Excel, keep your hands up. Do you have Windows? Keep your hand up. There you go. It's pretty much everybody. Well, so I like Excel as well, right? So something Excel spreadsheets have done really well is a conceptual model that is really simple to interact with and understand, right? The idea of having rows and columns, that's something everyone can relate to. It's easy to access information. It's easy to update it. It's easy to read it. And relational databases, that came up in the 70s, decades ago, also built on this model of having rows and columns. So that's something that's easy to relate to. Now, the reality that we have today is that not everything fits into a two-dimensional array or a table. So let's say you want to build a payroll system that, in New York, financial services are really popular. I'm just going to guess, right? So lots of banks that have international offices. So you have a workforce that is maybe in US, in Japan, in China, in Europe. Every country has different rules when it comes to taxes, how you record information about your employees, how you issue your payslip. So can you think of a unified schema that's going to work for every country in the world to build a payroll system? That's just not going to be possible, because you're going to have so many optional attributes, so many null values, and when requirements change, how do you update that schema? So two-dimensional tables are not suitable for those type of environments where requirements are frequently changing. Not only that, graph structures are becoming increasingly popular in terms of processing, so doing network analysis, for example, whether it's social media, or whether it's protein interaction if you're into kind of chemistry and biology, or fraud detection, who's connected to who, do we trust this party? So the data we have today is a lot richer and is a bit more difficult to store in a two-dimensional table, right? So a graph, how do you store that into a table? You can potentially make it work, but it's really inconvenient to work with and query. And that's the point, is that we need new technologies that not only can cope with volume and velocity, but allows us to be productive when it comes to data processing with data that comes in various shapes and sizes. Now, I've got a good and a bad news. The bad news is if you look at this scary table, each little logo is, one new technology, one new database, one new thing that allows you to solve a specific problem dealing with velocity, volume, variety, maybe all those three things together or just one of them for different domains. So there's a ton of stuff. It's scary. And Spark, so this is like Find Wall-E, right? The Spark logo is somewhere here. Yay, that's Spark. So today we're going to talk about Spark, but there's a lot more going on. So the good news is, if you want to be a big data engineer or big data consultant, you can make a lot of money because no one understands it. There's too much. So that's good from a career point of view, I think. So that's a great justification. So I've given you the landscape. Now I'm going to drill down a little bit and focus on two classes of big data problem. The first one is batch processing. And that's the idea that you've got a ton of data at rest. And you want to process it, making good use of your existing infrastructure. Okay, so maybe you have a cluster machine, you want to make good use of those resources to produce some information based on data at rest. So let's say, for example, you want to calculate a monthly payroll, right? So you take all your database of employees, the salaries, and once a month you produce the payslip. That's an example of a batch processing job. The data is at rest. If you want to train a machine learning model, maybe you go fancy and you go deep learning, you've got all those images sitting somewhere, right? Again, the data's at rest and you train your model on it. That's batch processing. You want to make good use of the resources you have in your infrastructure. So different servers, different computers with different hardware characteristics and coordinate them to produce a result. And again, in the financial services, compliance is really exciting and really hot. And for example, you may wish to take the inventory of all your trade orders and produce the appropriate compliance. So again, the data is at rest. Okay. So you're not so concerned about the latency, so how fast the thing executes and you get a result. What you're concerned about is making good use of the resources available to produce the result. And often, volume is the concern and variety. You might have a ton of different things like log files, JSON files, spreadsheets, and you need to kind of merge it all together to produce some insights. Now, the other class of big data problem is called stream processing. And here the concern is often the latency. So how fast do I get a response to a specific query? So you typically have an SLA that you need to be able to manage. So in terms of hundreds of milliseconds. So for example, if we have a bank transaction, so I think there's a lady at Stripe yesterday that was talking about fraud detection for Stripe transactions. You kind of won't be able to flag it on the spot whether the transaction is fraudulent or not, rather than wait a couple of days because the money is gone, right? So in this case, latency is very much the concern. And this is even more challenging when you have high velocity. So when you have millions of transactions that are all happening at the same time, how do you combine velocity and latency together? And there's a lot of kind of maybe newer technologies that are dealing with stream processing problems that you see. And Spark actually can be used for both batch processing, which that's what we'll focus on today, but also for stream processing. And often when you do stream processing, you have to think about time windows. So all the transaction between now and in a second and aggregate that, right? So that's kind of like the intuition. So the data is in motion, you've got high velocity, and you need low latency. So let's do a little quiz, just to make sure we're all on the same page. I've got prizes, actually. So this is my book. Functional Programming in Java. I appreciate it's a Python conference. But what I hear is often people write Python code, and I code in Python. But once you go to production, often some companies are debating whether they're migrating their code to Java or not, because they can buy into the whole JVM ecosystem that allows you to monitor your job and do some performance tuning. So those are the prizes. So let's see. Generate a balance sheet from all the invoices in a month. Is it batch or is that stream? Batch, right? The data is at rest, and we need to compute a balance sheet based on that. Now, provide real-time alerts to stock market changes. Stream, right? You kind of flag now where it's going to go down, it's going to go up, or whether there's an anomaly, and we should think about some strategy. Build a PageRank metrics for the web. So the PageRank, the classical algorithm invented by the Google co-founders to tell you how popular or relevant a website or web page is, right? And the way that's calculated is by aggregating multiple websites and pages together that are linking to this web page. So is that batch or is that stream?
Both.
Yeah, it could be both. So let's think about it. So in practice, a lot of problem can be both if you think about it, right? So the reason you may say it's batch is because the input to this function to calculate the page rank is basically the internet, right? That's pretty crazy if you think about it. Here's the whole internet indexed, and we'll calculate a number based on that. So the data is at rest. Now, indexing the internet takes time, right? Because there's a ton of data. So in practice, it's a batch processing job. The ideal is that PageRank metric for every website is continuously being updated as the internet evolves and people post new links and so on. So we'd like it to be a stream processing job. But from an engineering point of view, because you're dealing with the internet, there's always some sort of latency. So it'd be classified as a batch processing job instead. Now you can be really clever with incremental updates and stuff, and then it gets a little bit more confusing whether it's batch or stream. But you can think about this problem as both batch and stream. And the last one. So by the way, machine learning for cybersecurity, really hot as well, tons of money. So anomaly detection in network traffic, streaming. Potentially it could be both. In practice, you want to be able to flag whether you have some sort of intrusion anomaly like on the spot so you can react to it. It could be a batch processing job if here's a log of network traffic and then you need to do some analysis on it. But if you need to detect that maybe with a firewall rule, then it'll be classified as a stream task.
Although a baseline can be determined based on the batch, for example.
Sure. Cool. Awesome, everybody. So that's kind of like the big data landscape, the two main classes of problems. And what I'm going to do in this tutorial is to focus on batch processing using Spark. So let me introduce the Hadoop ecosystem and the technologies available that you often hear about, and then we'll get hands-on and get coding. So how do we deal with big data? Well, we take Anthony's computer, do some processing, and it's too slow. We're unable to cope with the business requirement. So what's the next thing we do? If we want to speed some task, what's the immediate option available to us?
I have a bigger computer.
Huh?
I have a bigger computer.
Yeah, more power, yeah? Go bigger, great. So scale up, woo! So if you got money, that's great. And there's a very good reason why this is the thing you always, most cases, want to be doing. The same code that you write on one machine in Python, it's going to work on a more improved version of that machine, right? So maybe the frequency is higher, you've got multiple cores, you add more RAM, you've got SSD, you go bigger. The same code will run. And that's fantastic. You don't need to do any configs, any setup, all that kind of stuff, right? So often scaling up, is the solution that is recommended in terms of solving the problem. And it's really easy to do that these days with cloud services, right? In the click of a button, you can upgrade a machine, right? And you might want to rent it out for a certain number of days or hours, depending on what processing you need to do. So that's the fastest thing you can do. Now, eventually you hit a ceiling and it gets increasingly more expensive just to add a little bit of performance. So if I was to draw a curve, the return investment goes like that. If you want just an incremental performance improvement. So the next thing we can do is to scale out. So everyone in this room, we're all going to use all the computers, and somehow we're going to coordinate, split the jobs, merge it, and hopefully solve the problem, right? That's the next solution. And obviously, there are trade-offs for all the solutions. So on the left-hand side, you have high usability. You can code on one computer, great, pandas, we love pandas, or Spark, that I'm going to mention in a bit, and it just works. If you go on the right-hand side, you get a lot of power, potentially infinite. We can scale out on demand. However, it's a lot more complicated to deal with a lot of machines as opposed to one. So the classic business intuition, if you're managing a team, often it's easier to work on your own than like with 10 people, right? Suddenly you have to coordinate who does what. You need to have your one-on-ones and whatnot, right? So that has a lot more overhead as well to solve a task. So that's the trade-off. Now, if I was to draw a list of pros and cons, scaling up is my favorite one because it's the same programming model. I don't have to worry. I can just run the same code. I don't need to change it. But often, from a business point of view, it means you invest into a high upfront cost, so we have to buy into a more powerful machine. Nowadays, with cloud services, obviously, that's less of a concern. You can have more power on demand, so that's good. You have a single point of failure, so if that machine goes down, you're stuffed. And you have a ceiling in terms of how much performance you can get, right? Just based on current physics. Now, scaling out is more difficult to use, again, because we have to coordinate, split the work, merge it together, and we'll talk about Spark. Potentially it's cheaper. We can get a lot of cheaper machines to work together, as opposed to investing into one larger machine that is more expensive. You get flexibility, so we can adapt with the demand. So, if you think about Twitter, when there's a football game, people tweet, so, we can get more machines to process the tweets. If it's a quiet day, it's raining and everyone's home, then, we can scale down the number of hosts to do the processing, right? So that's what you get. You get an elasticity property. So where does the Hadoop ecosystem come in? So wouldn't it be nice if we had the best of the two worlds, like usability and power? That's kind of what we'd love to have. So what the Hadoop ecosystem is all about is a set of technologies that gives you the illusion that you're working with one machine or one unified interface, but under the hood, you have a distributed system. All right? And that's the only thing the Hadoop ecosystem is about. And obviously, it gets a little bit more complicated because there's multiple concerns when you actually need to do some sort of computational work. So here's like 3 layers that you can think about. So if you need to process data, you have to store this data somewhere. Right? That's like the first thing. So if I think about my MacBook Pro here, running macOS, then I've got a file system that allows me to store data. So how can we get a file system that allows me to store data on a cluster of machines, right? And that's called a distributed file system. And HDFS, which stands for the Hadoop file system, is an example of a distributed file system. So you'll get an interface, read and write for files, but the data is stored across multiple machines. There is fault tolerance, so certain slices of files will be copied over several machines. When you try to read, I'll be smart enough to realize, I can get a slice from here, and in parallel, I can get another slice from here and load them up, right? So that kind of stuff is abstracted away for you with HDFS. So that's good. And Amazon, if you use S3, a lot of vendors have their own proprietary distributed file system. This is the Hadoop one. Now, the next level of in that layer is you can think about, so YARN. Isn't that a great acronym for dinner parties? Like, what does that even mean? So it means yet another resource negotiator. The tech industry always comes up with like random stuff. So on my machine here, I need an operating system that is capable of dealing with the resources available on my computer. So the memory, the CPU, maybe a GPU as well, if we go fancy, right? So we also need this idea of an operating system for a distributed system, right? Now that's often called a cluster manager. So that's going to decide, all right, I know all the resources available in my cluster, and I can allocate certain resource to execute certain jobs, right? So that's yarn. And there's other cluster management. Mesos is also a popular one that you may hear about. Now, the next layer is actually, how do we execute some work? Like, I just want to write code, right? Like, so what happens? So that's the data processing layer. And there's two data processing engine that a lot of people talk about. We'll talk about Dask as well. So there's a tutorial later on about Dask, and I'll come back to this topic in a bit. So you've got MapReduce, which is really old, obsolete, not like Terminator, who's old but not obsolete. And then we've got Apache Spark. So what those guys are going to try and do is say, well, all right, I'm going to let you as a developer and a data scientist specify a task, and that's going to get scheduled on that cluster using Hadoop Yarn. It's going to be able to read and write data using the Hadoop file system. So how do we compare those two things? It's crazy to think that MapReduce was only released in 2011. I just can't believe that. It's only 7 years ago, and it's just legacy. So MapReduce, again, is just a distributed processing engine. Starting in 11, has only two operations available, map and reduce, that lets you specify any kind of task. So there's a little bit of a problem here, because the reality in the world that we deal today, there's a ton of operations that we may wish to do, you know, like you do in pandas, things like filter, apply, grouping, reducing. You can create a rich list of operations. But no, with MapReduce, you have to fit within that framework. And on top of that, the way the implementation works, if you have to stage an output of one function to become the input of the next one, it's written to disk and then gets loaded back in for the next operation. So there's a high I/O cost. So as soon as you exchange data over the network, you write it to disk, it's super, super slow. So MapReduce doesn't perform very well. So Spark came about 3 years later and addressed some of those issues. So there's a richer set of operations, which means as a data scientist, you can write code that it's closer to the problem statement or the business requirements. And on top of that, it's going to try to execute as much work as possible in memory before it gets exchanged between several machines, right? So that's how we kind of reduce the performance bottleneck. So here's a benchmark. Benchmark, it's only one benchmark, right? But Spark definitely performs a lot better than MapReduce, and is widely adopted by most large financial companies and other companies today. So if you're not familiar with MapReduce as a concept, I'm just going to explain the intuition. So really the problem we want to solve is, how can I split a task and get several machines to work on those tasks independently so that I can get as much parallelism as possible, right? So I'm going to grab Anthony. What's your name? Jack. And
Joe.
Anthony, Jack, and Joe. Great. So, and myself, Raoul, right? So suddenly, we're given a list of transactions from a bank, and we're going to have to process it to find out the monthly spend, right? So that's the task that we need to solve. So where do we start? Because we're 4 people, so theoretically we could get that job done 4 times quicker. That's the ultimate goal, right? So the map step is saying, oh, okay, Jack, you're going to get a subset of that data. Joe, you get a subset of data. Anthony, same for you, and myself, right? So we split it in 4. Now the first operation to execute is probably some sort of extraction. Given transaction, how do we get the amount? How do we do some conversion? Because the transaction might be, in EU, in GBP, in Chinese yen, etc. So we're gonna have to convert that to dollars. So there's a bit of CPU work to do. And that's map. So map says, there's a function that you need to apply on the subset of data, and it's completely independent. So all of us here, we can do that work completely independently. And that's awesome. Like, that's the best that you want to have, because there is no overhead to communicate and share results. So you get a great reduction in latency. Now, at some point, because we found an intermediate result, we don't have the monthly spend yet. We all have some information about it. we're going to have to kind of coordinate to merge it together. And that's called the reduce step. What reduce means is, we're going to have to decide, either you and I are going to do that final kind of merge. So I've got a quarter of the information, you have a quarter information, you've calculated the total for that quarter, and then I hand over to you, and now you get a half. And you two do the same, you also get a half. So that's called reduce because we went from 4 to 2. And finally, you guys decide who does the final half, right? And then we have the final result. And that's how you get parallelism. So MapReduce is applicable both in the context of multi-core programming, where you get different threads that are doing the work in parallel, or in the context of distributed system, where instead of a thread, you have a machine, right? Now in practice, what happens is, not only you get distribution, but each machine is also multi-core, so kind of this concept trickles down. But that's the MapReduce pattern, and that's why it's so popular in functional programming and in parallel programming. Cool. So that's it for the Hadoop ecosystem. Hopefully everyone gets an idea of what it is. And what we're going to do now is to Spark. So Spark is, again, a distributed processing engine, and we're going to focus on batch processing. So let me introduce Spark before we get a notebook going. So Spark is really a unified data processing engine. The reason I say unified is because it supports multiple data sources. So Spark is really useful when you have unstructured data, for example, which might be log files. So all the HTTP logs in a web server. There isn't structure per se. There isn't like a schema that you're going to draw. It's just text, right? So you could load all those log files into Spark and start to do some work. But it also allows you to interact with things that are a bit semi-structured, I guess, like JSON. So JSON files can have a schema, or they can have a lot of optional attributes. So you can load that JSON into Spark. You can plug Spark into a relational database as well, right? So any sort of data sources, you can read that into Spark and use Spark as your distributed processing engine. Now, Spark is supported by multiple programming languages. That's definitely a great win when you're a large company and you want to buy into a technical solution, because often you might have a team of developers that use Java, for example, right? So if they know Java, that's great, they can use Spark. Or you might have people that know Python, that's great, they can also use Spark. So there's a Python API, Java API, Scala, and nobody uses R, so don't bother about that. Everyone should use Python. This is PyData after all, it's not R data. So I'm just kidding, of course. Now let's say you've got Python and you've got different data sources that you want to plug in. So what's available? So there's different components within the Spark project that you can use. So today we'll focus specifically on Spark core. So the RDD API that allows you to plug into unstructured data and also structured data. But you've got things like data frames. So if your data has a schema, and you want to run SQL-like operations, then the data frame API is really performant because there is a known set of operations. You can run SQL on Spark. You can do streaming. So things like window slicing. So I want to batch up transaction over seconds or 5 transactions over time. Those windowing operations are available in streaming. You can do distributed machine learning. So there's MLlib, which is a bit old now. There's Spark ML, which is kind of the newer version. You can run graph queries as well using GraphX. So it's a fairly rich set of tools that allows you to do data processing depending on what the shape of your data is. So how does it work under the hood? So here's a bit like the life cycle when you want to run a Spark job. So it always starts with a driver program. So that's like the program that's going to launch the job, right? So we call that the driver program. And the driver program has to set up what we call a Spark context. So that's the entry point to using the Spark API. So later in the notebook that you'll walk through, you'll see a Spark context, right? So that's the entry point to run queries. Now the Spark context is going to interact with the cluster manager, and the cluster manager is going to deal with resource allocation, schedule different jobs on those machines, aggregate it back, and then send the information back to the Spark context. Okay? Now, I just want to spend a bit of time on PySpark and put a big caveat. We're using Python. Do not expect the same performance as using the Java API, because there's a ton of wrapper and things that are happening under the hood. So as I said, Spark is a Java project, runs on the JVM, right? Now, if you write Python code, and suddenly we need to execute this Python code on JVMs that all set up on each machine in my cluster, there's going to be some sort of serialization. So we're going to have to convert the Python object world into the Java object world, right? And that's expensive because you waste CPU in doing the conversion, and you waste memory allocation and memory access for kind of interacting with this serialized data. So PySpark is always going to perform worse than just using the native Java API, just because there's a lot of memory overhead to do this serialization. Now I have to say, some of that is being reduced. So the Python API is going to try to do as much processing as possible in Python and reduce that data in Python before it gets exchanged to be run on the JVM. So there's a little bit of smartness that is going on, but ultimately there's a lot of overhead for converting between Python and Java, right? So not only that, even worse, when things blow up, when things go wrong, you're going to see a nice Java exception or a Java stack trace, because the job runs on the JVM, right? So if there's out of memory error or there's some problem in your data, then you'll see a big fat Java exception. It might be like, whoa, like, I don't know Java, what the hell is this, right? Which is totally understandable. And this is why I also encourage you, if you're interested in big data processing, to come to the tutorial on Dask that is happening this afternoon, not by me, by another gentleman, because Dask is essentially a fully Python project that attempts to be the pandas for distributed processing. And there's a couple advantages here, is that if you're already a data scientist and use pandas, the conceptual migration between that and Dask is fairly trivial because it's the same API. And secondly, when you get exceptions, there'll be Python exceptions as opposed to Java exceptions, okay? However, the JVM is great, again, in terms of monitoring, profiling. It's well understood, has been around for almost 3 decades now. Any company has a Java running somewhere in a JVM, so it's well understood. There is support available. So those are all concerns that are really important for production. That might be really cool to play around, but it's still an experimental project. Okay, excellent. So that's the scene. Let's now look at the Spark API, so the RDD API, and we'll learn the different patterns available. To get started, we'll process data on each computers. And at the end of this tutorial, I'll show you how we can take the same code, set it up over a cluster of machine, and massively reduce the latency of a request or deal with like a large volume, okay? So just to learn, everyone's gonna work on their computer, but then later on I'll show you how we can like scale this out to several machines. So RDD means Resilient Distributed Data Set, another fantastic acronym for dinner parties. And you can think about it as just a collection of elements, so a bit like a Python list. But the beauty is that the data being computed is distributed over multiple machines. So that's abstracted away. You get the illusion that you just see an interface, a list. But under the hood, all those operations that will apply on an RDD will get scheduled over a cluster of machines. Okay? So, really simple. If I want to create an RDD from the Python world, I can use this method called parallelize. SC means the Spark context. If you remember, the Spark context is declared in the driver program. That's the entry point using Spark. That's an object that you would be creating if you wanted to use Spark in the notebook that's set up for you. And then what you get is an RDD. So parallelize is not very useful. It's just useful for learning and toy examples. In practice, you're going to need to load some data from somewhere and then use Spark as your processing engine. So there's a few methods available. Text file, that's going to take a file from a location, and each line becomes an element of your RDD. Okay, so I could potentially process a large file over a cluster of machine just by using text file. It supports various data sources. So for example, if I wanted to load a file from an S3 bucket, if you're using Amazon, so S3 allows you to store large files up to 5 terabytes. You know, I could, with one single line of code, load up a large file from S3 and start using Spark to process it. Okay, so that's pretty neat. There's very simple operations, you know, that you may use. So counting returns number of elements. Take returns the first n elements in your RDD first, just the first one, just a couple of basic operations to get you started. Now, where things get more interesting, it's kind of like common data processing patterns that you may be familiar with if you're using pandas. So the first one is filter. So that's a bit like your where clause in SQL. And remember, here we're potentially dealing with data that is unstructured, coming from log files. Okay? So this is why we have those lambda expressions. So those are arbitrary pieces of code that we want to be able to run on each element in the RDD. So filter here is going to say, well, give me all the names that start with J, and you know we've got Jack and Joe here, so that's pretty convenient. So in this case, you know, Jack and Jessica are the one that is kept. Now I want you to understand that filter is not a mutable operation, so it's not changing your data source, it's just filtering those elements out. So we're going to have a new RDD that has the elements. We never modified the source RDD or a list, right? It's just the values flow through. Map allows you to specify one operation on each element of your input RDD. So it's a bit like apply in pandas. So here I want to say, you know, transform each of the strings to uppercase, and you can see the output here is all those names are in uppercase. Okay, excellent. So the power is when you really ooh, that's interesting. There we go. The power is really when you kind of compose all those operations together, right? Filter and map, produce an RDD, so you could chain those operations up to solve a specific business problem. Now, flat map is the one that is conceptually a little harder to grasp at first. So if you come from a functional programming background, flat map is highly popular. The reason is it allows you to specify one-to-many relationship in mapping. So if I look at map, clearly you can see from one input we get exactly one output, right? So Amelia in lowercase, we get Amelia in uppercase. So that's one-to-one. Flat map allows you to do one-to-many. So that could be 0, could be 1, or it could be several elements. So here the method split in Python returns a list. Okay, so if I do split over I on Amelia, what you'll get is a list with 2 elements. A male being the first element, and then just A as being the second element. Okay. Now, if I do the same thing on Jack, you know, Jack there's no I, so you just get a list of 1 element. Jessica, you get Jess and Cal. So what flatmap does is to apply a map operation. So the function I would pass as an argument here is applied on each element on the left-hand side. That returns a list. And the flatten part, flat, essentially collapses all those nested lists into one single RDD. Okay, so what you get is still a flattened RDD, but clearly we've achieved one-to-many mapping here because the result here has more elements than the input. Okay, so that's flat map. Distinct allows you to remove duplicates. So here's a few operations available. And in the Spark world, there is a difference between transformations and actions. A transformation allows you to produce another RDD. So filter, map, flat map, distinct are all producing RDDs. And that means you can chain those things up together to build a rich queries to solve a specific task. And action, that's when you actually trigger this pipeline of operations to return a single value. So count is an action because you get a number at the end of it. Take is also an action because you get a Python list at the end. And filter is a transformation because that produces an RDD. Okay? So let's go to the Python notebooks now. So again, you can use the Google Colab, a link that I provided to you. You have to run all those initial cells here. So that's basically setting up JDK, Spark, downloading the dataset, setting up the config, so you're all ready to go. All right. Now I'm going to use my local notebook to show you what's going on. So this notebook is if you downloaded the repository from the GitLab. Okay. So the first thing I'm going to do here is to set up my Spark context. So I'm ready to go. Okay. So now, as a little simple exercise, we're going to have to do two things. So one is create an RDD from the Python list, just get warmed up. And then throughout this tutorial, we'll do a bit of basic natural language processing on an essay called War and Peace. Okay? So I see some smiles here, so some people know about War and Peace. That's good. So we're going to do some bit of mining on that text. So, just to get started, just so everyone gets an idea. So Paralyze, as I said, allows you to take a Python list and turn this into a RDD. So we've got Anthony, Jack, Joe. Okay, so that's going to be an RDD. And now, if I look at the type of that, what you'll see that returns me a PySpark RDD. So that's a class that is built into the PySpark project. Okay, it's a resilient distributed data set. So now using this RDD, you might be tempted to say len of RDD. That's not possible, right? Because len works on Python list. Here we have a completely different type. So we're going to have to use the RDD API, so rdd.count, and that's going to produce 3. All right? So very simple. Now, things get a bit more interesting when we can actually load up some data file and process it. Again, on one machine at the moment. So this is running locally. And then by the end of the tutorial, I'll show you how we take this code and set it up, this up over a cluster machine. So I can say text file as an input, get the URL of the file. So we're going to call this lines, right? And now I can say lines.count. And what we'll see, there's about 54,000 lines. Excellent. So what I want you guys to do now for like 5 to 10 minutes, and then I'll live code it, is have a go at those learning activities from basic RDD manipulation to using filter, map, and distinct. So all the way here. And hopefully the Google Colab link is working out. Remember, you need to say open in Playground, run all the cells, shift enter to run a cell, and you should be good to go. So I'll give it 5 minutes or so for you guys to have a play, and then I'll walk through it. If you got some questions, please come here with your laptop if you need some assistance, and I'll try and help out. Hey man.
I'm getting this. I got that from the Gmail link. Is there another place I should go?
Yep. So just type this link here. This one. Type that in your browser. Then you should be like all good to go. Requires you to have a Gmail account, which you do, I think.
Yeah.
Let's see if that works. Okay, if you open in Playground. Cool, and then shift enter. And Does it run anyway? Yes. Cool. That's setting things up, and then you should be good.
Great, thank you.
If this works, I'm so happy. Did anyone get the Google Colab thing to work? Raise your hand. Oh my God, yes. You have no idea how much hassle setting up Spark has been in the past. That's so good.
The GitLab link wasn't working for me. The GitLab link wasn't working for me earlier.
Oh, Jesus. Okay.
How the collab notebook is working?
Oh God, yeah. Well, everybody use the Colab one. Why is the GitLab not working? Some sort of DNS settings, which we'll look into. But you have everything on the Colab, so that's all good. Tu sais pourquoi ça marche pas? De quoi j'ai pas mis en place? Le GitLab.camel Spark, ça marche pas. Ça marchait ce matin. Mais ça marchait ce matin, quoi. Do not record this. Shit. Can you like cut? Oh well. Is that cut? Cool. So I'm just setting things up, and I don't want that to go on YouTube. Yeah, bro. We pass as an argument a function that's going to apply to each element. So that function is a predicate. It returns true or false. And then we're going to say war in get words, that line. So I can do a count on that. So we can chain things up. So that's my war count. Now we can do the same for the piece count. So take our lines, filter, underline piece in get words. The line, we can count, and then I might wish to like get an idea of how it compares. And at times peace occurs less frequently than war, so that's not cool. But at least we know how to solve this problem using filter and count, so we can apply a transformation and then an action. Now let's look at map. So use map to capitalize each line in the RDD. So we get the lines. Map, we get the line to upper, so we get a one-to-one mapping. Then I'll take 15, and again, I can iterate over this result and print it. Okay, so as you can see, everything is in uppercase. Awesome. Now use flat map to create an RDD of the words in warrior piece and count the number of words. So that's a little more tricky. So let's try and divide this problem in different steps. So I'm gonna use map first, just so we get an idea of what we might get. So if I use map, right, and I do lambda line, and then get the words on that line, okay? I'll take the first 10 results, so we get an idea of what's produced. So if I do this, what you'll see is that we get a list, right? So this outer square bracket means we have a list as a result, and then we've got like a closing square bracket here. Now, each element is another list. Why is that the case? The case is because getWords returns a list, as we've established earlier on. So, hello NYC, you know, if I do type of getWords, here, see it returns a list. So that's why we get a list of lists, which is not extremely useful, because if I do a count here, we get exactly the same result that we had earlier, which is the number of lines. So that's not useful, right? So somehow we need to go from the list of lists to a flattened list. And that's what flat map is for. So again, if I take 10 here, we get that. Let me just use flat map instead. And what you'll see is suddenly very nice. We flatten all those intermediate lists, and then I can take the first 10 words. Now, what that means is the RDD that's produced here is essentially the words. And I can do a words.count, and we can see it's, you know, larger than the number of lines, and that makes total sense. Cool. Now, what about the count of number of distinct words? Well, we've got a nice distinct methods to do that. So I can say distinct. And the reason it works is because words is an RDD. And I can apply a transformation of that, which gives me an RDD, so distinct, and then I can do a count. Okay? And then we can see there's about 19,000 unique words in the essay. All right. Thumbs up, everybody? Cool. So I'm going to cover a couple of more queries available. Just so everyone has kind of an idea of the set of operations available. So it's one thing to work on one RDD and one file. In practice, you'll often need to work with multiple data sources and combine the data sources to solve a specific task. So I might have you know, customers from one department that are really interested in sports. And then I'll have another source of customers that are really interested in food. Okay? So I may wish to kind of combine those two sources together in order to do some business intelligence. So how do we combine two RDDs? And to do that, you've got a union method that essentially concatenate two RDDs together. Okay? So that might be two log files that you're loading up, or you're reading off this information from some database. Now, intersection works a bit like in set theory. So here maybe I'm interested in finding out what are my VIP customers, the ones that are highly engaged because they're buying from those two departments. So by doing intersection, I can find out that Jessica is available in both RDDs. Okay? And subtract allows you to remove elements from an input RDD. So maybe you have, I don't know, like a list of suppliers, which is your names one, and you've got some trusted suppliers that are given as an input, and you do your annual review. So you want to have all your suppliers except the ones that you really trust, right? So that's where subtract can be used. So we left with Amelia and Jack because Jessica was removed. She's a trusted supplier. Excellent. So those are a couple of operations that let you work with multiple RDDs together. Now, other operations that may use, so we've covered count, we've covered take. Finally, there's collect, which I haven't mentioned yet. So collect allows you to take an RDD and get the whole thing as a Python list. Now, this is an extremely dangerous operation, as the gentleman over there knows. The reason it's very dangerous is you're basically saying, I've got an RDD that potentially is distributed over a whole cluster of machine, and the Spark context, the driver program saying, awesome, just give me all the result, right? So if this is potentially a large amount of information, then you'll just blow up the driver program because all that data is going to come to one single machine and live in memory. And that runs on the JVM, so it's highly likely you'll have a memory error that will be thrown at runtime. Okay? So collect, to be used with care and practice, you shouldn't really use collect. You would dump result into a file or another data source to read the result later on. Reduce. Reduce is a fun one. And that allows you to merge and combine intermediate results from different places and get one output. So I don't have a whiteboard, so I'm gonna explain reduce in a cell. So we're gonna learn about reduce. Mark down. Boom. And then we'll insert another cell. All right, so let's say we've got some transactions. Transactions equals, where's Anthony? Cool, sorry Anthony. What do you like to spend your money on? Food? Great. What do you have for breakfast today? Fruits. Oh, that's very healthy. So how much do you think you spent on fruits this morning in terms of breakfast? Zero? Well, where do you get this deal from? Oh, you got it from here. Clever man. Free food, love it. I don't know. Like, let's. I need some numbers from you. So let's go for $5 of fruits. Clearly, you've got a cap, so you buy clothes, I guess, right? So $30 in clothes. Do you live in New York? What's the rent in New York like? Too high. Huh? 1,300. Awesome. Everyone's like, where do you get this deal from? Excellent. And maybe, do you have a gym membership? Huh. Right, one last thing you spent money on. You can't just be fruits and rent. Oh, yes. I don't know, $50 in beer, a daily spent. Excellent. Now, so that's your transactions, and what I want to do is, in practice, if you've got transaction from a bank, you have like billions of records, right, and you need to process that. Now, I want to be able to reduce this list into a single value, maybe the total, the maximum, the min. So how can we approach this? So I'm going to create a function called reduce. I was going to take some data and then a combiner. And combiner is going to be a function that abstracts how do we combine two values together to produce a result, right? So what ideally I'd like to do is to combine 5 and 30, and then the result of that combine it with 1,300, and then the result of that combine it with 50, right? So we kind of do like a little fold. So one way we might implement this is, we've got a result, and we might say we'll start with the first element, and then for the data, then we'll say rest is the combiner of rest together with the next element in the data source, and then we return the result. Okay? So what I've created here is just a simple function that iteratively combines each element in that list, produce a new value. We use that value to combine it with the next one. Okay? So in functional programming, this is called fold, because if you take a sheet of paper, which might be your collection, then you get those little squares if you keep on combining them, right? And you get one final element, like one little square. So the way I could use that is I could say reduce. Here, we'll take Anthony's transactions, data, and then I need to specify how do you want to aggregate each of these elements. So here I might have a lambda, which T1 and T2, so those two transactions. And I may say, let's just combine them, okay? So if I run this code, what we'll see is, we get our transaction. So where's data defined? But that's cool. So what we see here is the total of that is 1,390.
Yeah,
Yeah, so where do you see the bug?
line in code, you should start with the symbol data.
Double count.
You double count 0 and
Correct. So we'll do that. Oops. For the, sorry, yep. For the in data, and then we'll do that. And then there we go. So you're correct. So hey, my assumption with reduce is I'm starting with the first element, right? If the data source is empty, then obviously this is going to blow up because we can never access the first element. So often when you see libraries that implement reduce, there'll be an option to add a starting element in the case that your source is empty. So like a default value to use. Now what's happening here is that, we've started with 5, we combine it with 30, we get 35. We combine it with 1300, we get 1300, 35, and then finally we get 50. But the beauty with the reduced abstraction is that instead of passing this lambda expression here, I could decide to pass max, for example. And if I run this again, we'll see that the maximum is the rent in New York. Or I could say min, and then we'll see that it's actually the spent on fruits. So we've managed to build this really nice abstraction that essentially abstract the internal threading model, right? We're just saying, this is how you combine elements. I don't care how the iteration is done. In this case, it's a for loop, but the same abstraction could be used to reduce stuff over a distributed system. We just specify what is the operation to combine those elements. And that's why reduce is a really powerful function. And it's built into Spark. So it works like that, where reduce is a method. So it's called on an RDD, and then you give it the operation to combine those elements. Cool. So I'll give a couple of minutes to go through some of the remaining exercises. So you see there's a couple of set-like transformation, reduce, and merging filters. So I'll give a couple of minutes and then I'll live code this. We're running out of time. Cool. So we run out of time, so I'll just live code a couple of these. So use the function union section to create RDD of lines where piece mentioned. So we'll have the war lines. So get the lines, again we filter, lambda 9, we get war and get words in that line. Then we get the piece lines, piece, get words, line. And then if I want a union, I'll basically say war lines, union, piece lines. And I can do a count on this. We'll get 369, so that's the lines I have both war in there and peace. And if I do an intersection, then there's only 7, and I could collect them in this case, and then we can find what they are. So we can see here, to enter Russia, if I declare war, it will not make peace as, so yes, we've got those two words available. Now the next one is use reduce to find the longest word in war and peace. So if you remember, we have an RDD of words, and that's essentially we took the lines, we flat mapped that, and then we left with the words. So I'll do reduce, and what reduce get is essentially an accumulator, so that's the current longest word together with the next one in the RDD. So we need to kind of decide which one are we going to keep if we get 2 words. So I may say it's W1 if the length of W1 is greater than the length of W2, else we return W2, okay? So this is going to return one of the longest words, so we might have multiple words that have the same length, but they are also the longest. So this is a decision we made. So if I run this, then we'll see we're left with characteristically which is a pretty long word, if you ask me. Cool. Now, I'm gonna skip some of that stuff, and I'm gonna come to an example on using pairs for RDDs, and then I'll show you a demo and wrap this up. So I had a student one day, he kind of solved this problem of finding the longest words by using words. Then he did map. So at that point, you get a word, and I think he did something like that, word, then length of that word, okay? So what we're returning here, if you look closely, is a tuple, right? So that's just a Python tuple. We're gonna say lol, you know, and then 3. So not tuple, of course. We're gonna say, let's call it data. Now if I do data 0, then we get lol. If I do data 1, then we get 3, right? So we kind of have a tuple that's all 2 elements. So this student kind of returned a tuple here that contains the word and the length, and then call max on that. It turns out max is a built-in method into Spark, right? So when you run this, you get zoo, 2. So the result here is a tuple with zoo and then 2. But what's interesting is we went from an RDD of elements to an RDD of tuples. And that was possible by using the map transformation. Now, it turns out the reason zoo is the longest word is because Z and U, if you do this in terms of alphabetic order, right, it is the longest word. And I think what you can do with this operation, you can decide which part of the tuple to use to calculate the max. So in this case, we get characteristically a length of 18. So what I wanted to show you here is that using Spark, you know, we can support RDDs of tuples, of key value pairs, and there's new operations that are possible with that, group by key and reduce by key, that can be used as well. So here's an overview of the Spark API. And what I want to do now is to show you, right, that's great. We've done this on one computer. How does it work on a cluster of machines? So I'm going to use AWS. So that's the Amazon Web Services. You might be using Google Cloud or, you know, Microsoft Azure. And there is a service called EMR. What EMR allows you to do, and that stands for Elastic Map Reduce, is to create a cluster of machines where basically you give it a name, you say how many instances you want on that cluster. So M2X large is a specific type of machine. You say you want 16 nodes, let's say. Then you can configure the stack. So in this case, I want Spark, I want Yarn, all those things that I've mentioned earlier. And when you do that, you click on Create Cluster, and then a lot of stuff happens, and within a couple of minutes, you have a cluster of machines that is set up, okay? So I was doing that while you guys were working on the first set of exercise. So if I go to EC2, that gives me the list of running instances. So, you know, I've got a bunch of stuff that are Cambridge Spark things, but a ton of new machines here, M3X large, that were created on that cluster. Now, another service in Amazon is S3. So S3 allows you to store large files, and I've got a bucket here called humongous data. And I've got a JSON dump, which is essentially about 100 gigabyte of data, so 92 gigabyte. So that's, you know, JSON text records. And as a data scientist, you may have worked on a sample of that data locally, like we were, you know, doing, and then suddenly you want to scale your queries and your processing on the real deal. So how do we go about this? So that's where EMR comes in. So I've set up already a cluster. You'll see a PyData Neo cluster. And what it gives you is a couple of links. So one is called Zeppelin. So Zeppelin is just a notebook that essentially is the interface to your cluster. So you write some code in Spark, and the notebook is essentially your driver program. So that's really nice because the same Python code you've written, you can just like reuse it and just run it on a cluster. Now the other thing that you get is some monitoring tools. So Ganglia here tells me sort of the resource utilization in my cluster. So you can see here, I run some query not too long ago just to see if things were working. So the CPU went up because I ran a query. And then I can see the utilization over my cluster. Here you can see there's various spikes. That's because each worker node was doing some work as I run a query, right? So if you use Spark Notebook, you'll basically see something like that. Here I'm running a basic query, which you should recognize, right? So we say text file, text the URL to the S3 location. So that's my JSON file. And then I'm just saying count, right? And that's going to return me the number of records here. But obviously, I can use filter, map, reduce, distinct, flat map, union, and section, all those things that you've learned, and just run it here on that notebook, and it gets distributed over the cluster. Now, you may be curious why count is so slow. You know, it took 2 minutes to count 126 million record. You got to remember, this is just a raw file, right? So we don't have any notion of index. It's not like this is pre-computed. There's actually another operation called count approximation that is going to return the result really fast using the hyperlog algorithm. But the beauty of Spark, again, is you've got a ton of various files in different shape and sizes, complete and structured. You've got a unified API to process it. You work on a sample on your local notebook, and then you can scale it at the click of a button using EMR. So hopefully you learned something today. So that's the other tutorial. Just to wrap things up, we are from Cambridge Spark, based in UK, England, so we specialize in data science and machine learning training, especially on the corporate side, so do get in touch if you're interested. My colleague Kevin is going to give a really cool tutorial on interpretability of machine learning models using Lime, LR5, SHAP, some really cutting edge stuff to explain how decisions are made when you train a machine learning model. It's in this room, so stick around. And yeah, thanks everybody.